suppressed. Can someone help me in that?
Ria can certainly do this. Okay, Ria, over here. No, don't shout. I have my mic.
So basically, I mean, the time resolution is not so large that you really need this. So at the moment, the time steps are large enough. The AGN goes off immediately as soon as it eats something. The description when it eats something and what it eats, that differs. So in magneticum, the first thing is the black hole is not pinned. That means they don't merge immediately. They can get into 2 kiloparsecs distance and then they merge, which is basically twice the effective radius, the softening we anyway have. The good thing is that in magneticum it distinguishes between hot and cold accretion. So if there's cold gas, it's more efficient, goes off more quickly. For hot gas, it's a bit slower. That's not a time delay, more an efficiency delay. So, I mean, it's not perfect, but with the resolution we have, it works. If we go to higher resolution, we have to refine the models, and that's something we're working on at the moment. No, I think for the size, it won't make so much of a difference.
So I just wanted to comment on this as well. So in the Romulus simulations, the one that I talked about, so one issue where this delay time comes up a lot when you're dealing with transfer of energy to surrounding gas particles has to do with the resolution effect, where if you transfer all the energy from an AGN event immediately to a gas particle and then allow it to cool, presumably you're transferring energy to a very dense particle, which will then cool off very quickly, and your feedback will be artificially less effective. And that's a lot of the reason why lots of groups have gone to momentum-driven feedback, which doesn't have the same problem. However, in the Romulus simulations, we don't have that problem because we shut off cooling for a small amount of time, realistic based on the time step of the black hole itself. So you have more of a continuous transfer of energy that doesn't immediately get radiated away during a gas particle's time step. So we don't have a by hand burstiness in those in our model. I will say that in tests of different model properties, we do find that the burstiness of the black hole accretion. So this isn't due to this by hand approach, but simply due to doing Bondi-Hoyle accretion versus angular momentum dependent accretion, stuff like that. That can change how bursty your AGN accretion is, how bursty the feedback is, and that does affect the star formation history and the structure of the galaxy. Just like star formation feedback, how bursty that is, affects the star formation history and the structure of a galaxy. So yeah.
So can't you make it a little larger? I mean, even it's in the front, I can't read it. Okay. Well,
yeah. So okay. So many people remember. Okay. Is there a question? Another question? Till we blow this up, and let's go over there. So, please.
There's a question on a different topic, on the planes of satellites topic. So many groups study this in dark matter only simulation, and other groups study it in hydro simulation. Presumably there are differences or not. It's not clear to me, but I can't really imagine what kind of baryonic process could make a difference in the position of satellites. Can anyone help me in that? It seems like a very dark matter only kind of thing.
That's a good question. Okay, go over there. Answering.
Yeah, I think it's not so much changing the positions as it is what subhalos survive. If you have a disk, I'll talk about this on Friday, but that's going to destroy a lot of the subhalos, and although I'm still looking into it, it might do something depending on your azimuthal angle, basically.
But I think it's still an interesting question. If you think about that, only 0.1% of all halos are seen as satellites. I would wonder what is special about their orbit or their history so that they survive while the others don't survive. And I always thought if you see these rings or whatever, this might tell us something of why things survive and why others don't. And now with this all going away and there not being any rings anymore, I am again having to rethink. Let's start with Andre.
Yeah, so I think it was shown in the last couple of years that there are rings around other galaxies, and if you look at them visually in 3D, it's something that is easy to see by eye. If you actually plot the 3D distribution of galaxies within 10 megaparsec and just rotate it, that all these rings are aligned with a large-scale structure, with a local supercluster plane. This was shown formally by Libeskind et al. And by Brent Tully in the last couple of years. And therefore, whatever we think about the origin of these rings, observations tell us that they have something to do with local supercluster, because it couldn't be just random, right? These planes are aligned very strongly with local supercluster plane. So any discussion within like individual random halos probably will not lead you far, because clearly large-scale environment has something to do with these planes.
Yeah, the thickness of the plane is,
Well,
those planes is significantly
okay, so
larger,
if you see like 3 or 4 planes and they all have correlated orientations and they correlate with local supercluster plane, it sounds like it can be random, regardless of what you think about
Yeah, the
thickness.
question is more, if Pawlowski were posing the question to you, I think he would argue more quantitatively in terms of the thickness of the plane. The large scale, in terms of large scale structure, that thickness is significantly larger than what we're looking at.
I'm not arguing
for
about
the
that.
Milky Way.
I'm not arguing that thickness is not puzzling. I'm arguing that whatever the origin of
Sure.
these planes is and their thicknesses, it has something to do with local supercluster plane.
Okay,
Right?
so
That's a good point. I mean, because when we do satellites randomly selecting galaxy, that could sit in different environments. That's a particular kind of environment we have. And the same for Andromeda. It's the same environment.
Okay, I want to maybe address the question that was asked here about what baryonic processes, how they would cause a difference. One significant way in which they can cause a difference is in terms of angular momentum. Okay, so if you had a disk-like structure, that angular momentum could, would be preserved in a simulation where you include in a hydro simulation, but it would not if you just had a dissipationless simulation.
I wanted to change the subject to two very interesting observational results that were presented by Cheng Kai and by X Prochaska. And I wanted to ask them whether they could identify what they think are the theoretical issues that their new observations raise. So there are huge overdensities that they found. Is that a problem? Does this call into question the usual assumption of standard lambda CDM that the fluctuations are Gaussian? Also, for these bright Lyman alpha nebulae, bright and huge, is there a problem powering them? I noticed in the diagram that X showed that there's a bunch of quasars. Maybe that's the power source, and maybe that's also the source of a shock. But you've had a chance to think about your data for a while. So what are the things that we theorists should be learning, and what are the issues we should be thinking about?
I'll answer briefly. I think I'll refer you to Sebastiano's paper on the slug for the second line of questioning. I'll let Zhang respond to the first. And there he models in a numerical simulation with radiative transfer and so forth, and really couldn't reproduce the data unless he invoked a very large clumping factor that is not in the gas that's not being captured by the hydrodynamics. So I think at least that in that analysis it suggests that there's serious hydrodynamic issues not being captured, whether they have severe consequences for.
So now you have an even bigger Lyman alpha blob. The problems get worse?
I suppose, but it seems like the same problem to me at some level. Yeah.
And if the velocities on a scale of 100 megaparsecs, if the velocities on the scale of 100 kiloparsecs,
300s, yeah. Andy's got the number wrong there.
okay, if the velocities on that scale are 300 or 500, that's an enormous mass, and you're presumably only detecting the inner part. Is that a problem?
I don't believe anyone has simulated, if you like simulations, I don't believe anyone has simulated that level of cool gas anywhere.
I think it's more because you have to take protection into account. This is only 300 if you just what you see, line of sight, but yeah, but again, you know, in projection it could be much larger. Yeah. I think the problem is the angular momentum. On that scale, that fast rotating would be a lambda of order infinity. You know, you mean what? It's just simply too large. You don't get that much gas coming in with that amount of angular momentum. So
right. So for the protocast.
Yeah, if, and that's why it's not rotating. That's why it's just random counter.
Sorry. Can I go ahead? Right. So the high over density, if it's consistent with the lambda CDM model, I think it has a huge uncertainty because we only measure the over density of lemma alpha emitter, so there's a huge bias. So it's a huge uncertainty, like convert from the lemma alpha bias, emitter's bias to the bias to the over density of the dark matter, right? So over density is 10.8 for the lemma alpha emitter. 10. So from the current published lemma alpha emitter bias, I calculate that. So it's corresponding to a mass over density of 3 on 15 megaparsec. So if you compare with a cosmological simulation, you are expect to find 1 per 300 megaparsec cube, something like that. So our survey volume seems higher than that, larger than that. So I don't think it's contradict, but it's have a strong constraint, I think.
X, so is not like big overarching theoretical challenge with Lyman alpha blobs is existence of essentially warm gas, or what some people call cold, with very large velocity dispersions and in extent, right? So understanding how you get cold gas with such large velocity dispersions and such large volume is like challenge, right?
Just a comment on the Elon image that you showed, Jason, X. There were globs of whitish colors in the upper regions where in fact you had the largest velocity displacement, at least from where the quasar was. And I didn't know whether that was noise or if it's actually real. If it's real, of course, it's very significant. Okay, thank you.
Okay. Oh, yeah. Okay, so over here. Did we have
I want to follow up Andrei's question. What are the column densities that the hydrogen is supposed to be there? I'm asking because people have tried to do that at 21 centimeter very locally, do very deep integrations around in the halos of local galaxies and going down to 10 to the 17 or so, 10 to the 16, and they consistently never find anything at that level. But COS halos obviously does find neutral hydrogen, so I was wondering how the column density fits in this story.
Well, I think you answered your own question. What's the column density order 10 to 17 and the 18 COS halo scale? Pretty similar for gas around quasars. So then what was the...
So I was wondering... Yeah.
Yep. Okay. Like, put this here, and then in the meantime, I catch.
So this is a slightly different topic. So we had 2 or 3 different talks this morning about subhalos and trying to understand which, where the Milky Way might lie in the continuum of halos of our mass, and did we assemble our satellites early or late, etc. And I just wanted to, so the question was posed, are there other observations or other observational pieces of evidence we can use to try and pin down what the growth history might be? Concentration was mentioned as one. I think at some level stellar halos could be another one, in as much as that's the integrated debris from the satellites that we accreted at early times. And I think that's a potentially quite important one. And in that context, Milky Way's halo is amongst the smallest in the local universe for galaxies of its size. And so this is something that we may wish to, that doesn't sound completely inconsistent with the idea of the Milky Way having accreted most of its satellites late, that we didn't accrete a tremendous number early.
Andromeda has like twice or 3 times more big satellites than us.
Andromeda has 10 times the stellar halo mass than we do, but 2 or 3 times the satellites. I'm just like that, that's what's observed. But I think this could be potentially an interesting extra diagnostic. I don't know if we've really had a chance to chew on that as a community. But there must be, I think there are other ones too that we should bring to bear on this.
Yeah, because I think I agree with that. Some of those kind of statements about the satellites, because they look at the bright satellites, and we have tons of bright satellites on Andromeda. So you can apply the whole thing to Andromeda. There's no gap, for example, in satellites on Andromeda. Looks like us, but at the same time, it's so much different. So the same analysis should be applied to Andromeda. Just don't stick to us. Don't think that dwarf satellites are discovered only in the Milky Way.
I also wondered about this concentration business. If you have a late massive infall, and this massive object is still around in the outskirts, isn't it then clear that the concentration of the halo is lower because you added a lot of dark mass in the outer part? So by definition, the concentration must be lower because yeah, but the core radius might increase. So I just wonder if you add something to an NFW halo in the outer parts, would that decrease the concentration by definition because you added something new, or does it increase the concentration? So you know what I mean?
It decreases concentration.
It decreases. So then it's not necessarily two independent things.
We don't see big satellites at that distance.
Yeah, but when LMC is a big satellite and
not peanuts.
Oh, not big.
It's certainly the trend we see by analyzing simulations. When you have a big chunk of mass coming into a halo, the concentration decreases. But whether this is really due to your adding big chunk of mass at very outer radius, so that when you fit the density profile, you increase your RS. The reason I thought about this is because we look into where those massive subhalos are, and independently calculate the concentration by fitting the rotation curve of the halo. So what you see is actually the RS normally can be smaller than where the most massive, the significant subhalo is. So what that means is, although it's adding mass into the outer radius, but it doesn't really change the inner structure. So when you feed the RS, you still get the same answer.
I think we are getting
close
to pizza time or whatever.
Look, guys, if you don't like to eat, stay and we're going to discuss. Yeah.